Hello students. In the last class we discussed about the properties of electromagnetic waves. In this section we are going to discuss how to express an electromagnetic wave mathematically. So, expression for an electromagnetic wave. Imagine a wave is propagating along the positive x axis, and as we discussed in the previous section, if the wave is propagating along the positive x axis, the electric field will be along the y axis and magnetic field will be along the z axis. So, you can write like this: for an EM wave means electromagnetic wave. So, for an EM wave, propagating along positive x axis, the electric field is represented as vector E. Vector E is the electric field, and as I told, electric field is along the y axis. Therefore, I will write E y j cap, E y j cap, and this can be written as E 0 sin k x minus omega t into j cap. So, j cap is the unit vector which unit vector along the positive y axis. So, I will write the equation as vector E is equal to E y j cap, which is E 0 sin k x minus omega t into j cap. What is E 0? E 0 is the amplitude of the electric field. Amplitude means the peak value of the electric field. Amplitude of the electric field. And what is E? E means electric field at any instant. Instantaneous electric field at any instant. So, E 0 is the amplitude of electric field. K, the value K is called propagation constant. Propagation constant, and the value of K, the K can be given as K is equal to 2 pi by lambda. This is the expression for K. K is equal to 2 pi by lambda, where lambda is the wavelength. So, what is the SI unit of K? SI unit of K is this is 2 pi by lambda. So, this is in radian and the lambda is in meter. So, I can write radians per meter. Okay, that is K. Now, what is omega? Omega is called angular frequency. Omega is called angular frequency, and the value of omega can be given as omega is equal to 2 pi nu, where nu is the frequency of the EM wave. Omega is the angular frequency of the EM wave, nu is the frequency of the EM wave. So, omega equal to 2 pi nu, or you can write 2 pi by t. T is the time period. So, this is the equation for the omega. What is the SI unit of omega? 2 pi by t, radians per second. So SI unit of omega is radians per second. So this is the equation, and I have explained all the terms. Small t is called the instantaneous time, any time which they are giving. Capital T is the time period. So remember both. So we have written the electric field equation. Now how will you write the magnetic field equation? Let us see that. So I told magnetic field is along the z axis. Therefore I will write like this. Magnetic field is represented as vector B, which can be B z k cap, because magnetic field is along the z axis and k cap is the unit vector along z axis. So B z k cap, which is given as B0 sine kx minus omega t into k cap. So what is B0? B0 is the amplitude of the magnetic field, that means the maximum magnetic field, the peak value of the magnetic field. And as I told you, k is propagation constant and omega is angular frequency. Here also it is same. So this is the equation for the electric and magnetic field when the wave is propagating along the positive x axis. Now when I give the value of k and the value of omega in the equation, what will happen? So let us see like this. E0 and B0 can be written in another form. So I am writing like this: E is equal to Ey j cap, which is E0 sine, instead of k I will write 2 pi by lambda. So instead of kx I wrote 2 pi by lambda into x, minus omega I wrote, instead of omega I wrote 2 pi by t into small t j cap. Now 2 pi is common here, I can take 2 pi outside. So E is equal to Ey j cap, which is E0 sine, I take 2 pi outside, x by lambda minus small t by capital T j cap. So expression can also be written in this form. Similarly, how will I write the magnetic field expression? Vector B can be written as Bz k cap. So I am writing it directly, B0 sine 2 pi common, x by lambda minus small t by capital T into k cap. So this is the expression for the magnetic field B0. Okay, so these are the expressions when the wave is propagating along the positive x axis. Now what will happen if an electromagnetic wave is propagating along the negative x axis? Let us see. If an EM wave is propagating along negative x-axis, then the electric field equation can be written like this. E0 sin kx plus omega t into j cap. So earlier it was minus omega t, and when the wave is propagating along negative x-axis, the equation becomes kx plus omega t. Similarly, the magnetic field can be given as vector B is equal to Bz k cap which is B0 sin kx plus omega t. Okay. So the only change is the sign in between. Earlier it was negative, now it is positive. Now listen to me. Electromagnetic wave can propagate in y-axis also. It can even propagate in z-axis also. So if the EM wave is propagating along y-axis, how will be the equation? If the EM wave propagates along the y-axis, I can write this equation as E is equal to, so electric field will be then along the x-axis, okay? Therefore, I can say E is equal to Ex into I cap, which is E0 sin ky minus omega t. Here it was x because wave was propagating along x-axis. Now the wave is propagating along the y-axis. So I will write ky minus omega t into I cap. Similarly I can write B is equal to Bz k cap, which is B0 sin ky minus omega t into k cap. So the letter which shows here it is x. If I change that to y, the wave is propagating along y axis. If I change this to z, then wave is propagating along the z axis. That is how we make the equation. Okay. Now let us see what is omega by k. Omega by k. We already know omega is 2 pi nu. K is 2 pi by lambda. So I can cancel 2 pi and 2 pi. Lambda will go top. So I will get the equation as omega by k is equal to nu lambda. What is nu lambda? Nu lambda is called velocity. So omega by k is equal to nu lambda, which is equal to v. This is called wave velocity. So the velocity of the wave can be given by the equation omega by k. Now we are discussing how an oscillating charge produces an electromagnetic wave. How an oscillating charge produces an electromagnetic wave. We already told the charge should be oscillating and it should have non-zero acceleration. So imagine a charged particle oscillates to and fro. This is the mean position, and if a charged particle oscillates, here speed will increase, and when it reaches the end, the speed becomes 0. And again as it comes back, speed keeps on increasing, and when it reaches here, speed is maximum, and when the wave comes towards this side, speed decreases, and when it reaches here, speed becomes 0. So when the charged particle oscillates to and fro, the speed keeps on increasing and decreasing. That means the charged particle is continuously accelerating. Okay. Now, when the charged particle accelerates, what will happen? When the charged particle accelerates or charged particle oscillates, that oscillating charge will produce an oscillating electric field in its neighborhood. So the variation in the charge, variation in the speed will produce an oscillating electric field in its neighborhood. That means there is a variation in the electric field. That variation in the electric field will produce a variation in the magnetic field. So one will act as a source of the other, because when the electric field varies, that variation produces a change in the magnetic field. That change in magnetic field will again produce a variation in the electric field. That will again produce a variation in the magnetic field. So, first electric field varies, that produce a variation in the magnetic field. It will again produce a variation in the electric field. It will again produce variation in the magnetic field. That process will continue until the wave reaches the destination. So, I can say like this, one will act as the source of the other, and the electromagnetic wave propagates. The frequency of the electromagnetic wave is equal to the frequency of the oscillating charge particle. Okay? The frequency of the electromagnetic wave is equal to the frequency of the oscillating charge particle. Now, what are the sources of electromagnetic wave? The first source is the accelerating charge or oscillating charge, as we discussed now. The second source is an oscillating electric dipole. That is what we commonly use, an oscillating electric dipole. And the third one is LC oscillator. We studied about LC oscillator in chapter 7. The energy is oscillating between the inductor and the capacitor. So, DC is converted into AC. That is what we studied there. During that process, when we use an LC oscillator, the variation in electric and magnetic field is taking place. That variation is producing an electromagnetic wave. So, LC oscillator is another source of electromagnetic wave. So, if we are using LC oscillator, the frequency of EM wave can be given as nu is equal to 1 by 2 pi root LC. So, we can use this oscillator for generating an electromagnetic wave for radio transmitting station and television transmitting station. Okay, for radio and television to make the signals and to transmit the signals, they are using LC oscillators. So, these are the three sources. Okay, just please please make a note of it. The electromagnetic wave is discovered by Hertz. So, he was doing some experiment connecting that inductor and capacitor. At that time, he accidentally found out some wave was generating, and he discovered electromagnetic wave in that experiment only. So, we do not have the experiment to study, we only need to remember the name. Hertz discovered electromagnetic waves. Okay, so that is all for this topic. Thank you.